This call is now being recorded.
Good morning, students. In this session, we are going to discuss field tests. So, this field test is going to be conducted on a set of series missions. So one is series generator, another one is series motor. So, the series motor and series generator are going to be connected with each other, and we are going to perform the field test to determine the stray losses, and with the help of the stray losses we are going to find out the efficiency of the series mission when it is acting as a generator and when it is acting as a motor. Here, for conducting the field test, the two series missions should be, that is, the series generator and series motor should be of similar rating. So as both are of same rating, then only it is possible to perform the field test. Now let's see the nameplate details. DC series motor, it is of 5 HP rating, voltage is 220 volts, current is 19 amps, speed is 1500 rpm. Next, DC series generator, its ratings are also same, 5 HP, 220 volts, 19 amps, 1500 rpm. Both are of identical ratings. Now, the operators required to conduct the test is ammeters, voltmeters, rheostat, and loading rheostat, and tachometer. So, in order to fix the meter ranges, let's see the connection diagram. This is the circuit diagram that we are going to use. Here, let's fix the meter ranges based upon the nameplate details. It is a motor and it is a generator. Here, we are giving DC supply to the motor. The DC voltage is 220 volts that is available in our lab, and the voltmeter is connected across the supply mains. So it should be of range 300 volts in order to measure up to 220 volts. And this is plus terminal, this is minus terminal, and this is of MC type. Now it is a 2-point starter, and the rated current of the motor is 19 amps. So we are going to use 20 amps fuse as we are going to conduct up to floor conditions. The test is going to conduct up to floor conditions. Based upon the rated current, we are fixing the meter range, fuse rating 20 amps. Now, the ammeter 1 reads the current through the series motor. So, as rated current is 19 amps, we can use 0 to 20 amps MC type. So, current entering terminal plus, leaving terminal minus. Next, these are the armature terminals A, AA, and field terminals of the motor. So, YM, YYM. The motor field winding. So this is motor field and this is generator field. So generator field is represented by YG, YYG. Here we have connected one voltmeter across the armature and the series field winding of the motor. So this is plus, this is minus. So the voltage across the motor will be around 200 plus. So we are going to use 0 to 300 volts MC type, whereas the voltage across field will be very less. So it will be 0 to 30 volts meter is sufficient here. So this is plus terminal, this is minus terminal. Next, similarly, field voltage for series generator will also be very small. So it is 0 to 30 volts MC. Now, coming to the generator side, the generator load current is 19 amps. So 0 to 20 amps MC meter, current entering terminal plus, leaving terminal minus. This is a voltmeter, plus is connected to armature A, minus is connected to armature AA. So as the rated voltage of the Generator is 220 volts. We can use 0 to 300 volts MC type voltmeter here. So in this way, you can fix the meter ranges. And here we are going to use 2-point starter. As series machines are going to be started with 2-point starter, we are going to use 2-point starter here. Now, once the meter ranges are fixed, we can represent those readings here. So ammeter 0 to 20 amps. 1 meter we are going to use voltmeters 0 to 300 volts. Next 0 to 30 volts. 300 volts 3 meters and 30 volts 2 meters. Next rheostat we are not used any rheostat here. Loading rheostat we are going to use. And then there is one more circuit for measurement of armature resistance and measurement of series field resistance. So as we have already seen this in other experiments also, the supply voltage is 220 volts. Out of this 220, around 200 volts will be dropped in the loading rheostat. Only small voltage will be applied across the armature. So it is 0 to 30 volts meter is sufficient, MC, and ammeter is 0 to 10 amps, MC. The same fuse rating is also 10 amps. The same meters that we can use for RSA measurement. So 10 amps fuse, 0 to 10 amps, MC type meter, 0 to 30 volts, MC type voltmeter. Now the same we are going to represent in tabular column. Voltmeter 30 volts already there, and ammeter is 0 to 10 amps it is required. Okay, so after mentioning the meter ranges in the tabular column, the apparatus that completes apparatus part. Then we go for the experimental part. So here this is the procedure. So this is a circuit diagram. First, we have already seen the characteristics of series motors and series generators. In series motors, when it is operating under no load conditions, the load current will be 0 and flux will be 0, speed will be infinite. So under light load conditions or no load conditions, the speed of the series motor will be dangerously very high. It may damage the motor. So we should not start the motor under no load conditions. Under no load conditions, we should not start the series motor. So as the generator is acting as a load on the motor and electrical load is connected to the generator, by varying the load on the generator, we can control the load on the series motor. So the series motor should be started with at least 25% of load on the motor. Without load, we should not start the experiment. So before starting that means before giving the supply to the series motor, we should ensure that the load on the series motor is at least 25% as that of its rating. So after applying around 25% of load, we have to close the DPST and provide the supply to the DC series motor. And then under those load conditions, we have to take the readings of voltmeters V1 to V5 and ammeters A1 and A2. Those readings we need to tabulate in the described tabular column. So this tabular column, we have to note down the readings. Once we note down the readings, then we have to vary the load on the generator. So here, the load on the generator, by closing the rheostat switches, we can increase the load on the series generator. When the load is increased at different load condition, we have to take another set of readings. And then after noting down the readings, we have to go for another load condition. So like that, we have to go on, increase the load until the generator and motor currents will become near to rated values. So up to rated current from around 20% of load to full load conditions, we need to take 6 to 7 readings, 5 to 7 readings, or 5 to 7 readings should be taken at different load conditions. Let's take the readings as V1, 218, V2 203, 1 minute, 1st reading, to 18, to 12, sorry, it is 2 not 218 volts, V2 is 203, 5.2 volts, 4.2 volts, V5 is 218, 218 volts, 5.8 amps, battery is 11 amps, and speed is 1744. So go for second reading, 2, 212, 206. These readings got from experimental conduction of the experiment that we have conducted. So from that experiment readings, I am using here for calculation to 12, 16.6, 11.6, 1686, our reading to 14, 206, 6, 5, to 10, 17.4, 12.4, 40, to 14, 206, 6.2, 5.2, 206, 18.2, 12.8, 88, set to 14, 206, 6.4, 5.4, 204, 186, 15.2, 1570, to 14, 204, 6.6, 5.6, 202, 19, 18.6, 1536. So like this, we are going to take the readings. So after noting down the readings, we had to conduct armature resistance measurement and series field winding resistance measurement test separately. So this is a circuit diagram for obtaining the armature resistance. So here we have connected one voltmeter across the armature and one ammeter in series with the armature. The voltmeter reads the voltage across the armature and the ammeter reads the current through the armature. So by varying the loads at different intervals in terms of steps, we can measure the voltmeter and ammeter readings, and these readings will be tabulated here. So let's take the readings of armature resistance table. It is 1.6, 2, 3.6, 4.2, 5.6, 6. So the ratio of voltage to voltmeter reading to ammeter reading will give the RA value. So on taking the average, we'll get the average armature resistance. So it is 0.863 ohms. And similarly, we need to measure the series field resistance. So one voltmeter is connected in parallel to series field winding. It will measure the voltage drop across the series field winding, and the ammeter is connected in series with the field winding. It measures the series field current. Now, by varying the loading rheostat switches one by one, we can measure the values of voltmeter and ammeter readings. So it is 0.6, 2.1, 1, 4.2, and third reading is 1.6, 6.1. So the ratio of voltmeter to the ammeter reading gives the series field resistance. It is around 0.285, 0.238, is 0.262, and taking average we are going to get 0.261 ohms. So we have calculated the RA and RSC values. With the help of RA, RSC, and these readings that we have obtained by conducting the field test, we can able to measure the efficiency when it is acting as a motor for that is efficiency of series motor and efficiency of series generator. The MG set that we have used for motor, what is the efficiency? For generator, what is the efficiency that we can calculate? Let's see the calculations. So I'm doing the sample calculations here. So first, we need to find out the stray losses. So the total input to the motor generator set is V1 into I1. So V1 is 218, I1 is 5.8. 218 into 5.8. 218 into 5.8, it equal to 1264.4. Next, total output of the motor generator set V5 into I2. V5 is 218, I2 is 11. 218 into 11. 218 into 11. It's 2398. Sorry, it is 15.8. So here you are going to get wrong. To 18 into 15.8. To 18 into 15.8. 3,444.4 watts. This is output. The total loss is input minus output. Input is 3,444.4 minus 2,398. We are going to get minus 2398. We are going to get 1,046.4 as the total losses. Coming to the copper losses, I1 is 15.8 square. RA is, we got RA as 0.863. 0.863 plus RSC is 0.261 plus I2 is 11 square into RA is 0.863. We are going to get 0.863 plus 0.261. So When you simplify this quantity inside the brackets, you get 1.124 into 15.8 square. We're going to get 280.59. 280.59 plus 11 square into 0.863. We're going to get 104.423. So totally we're going to get 280.59 plus 104.423, 385.01 watts. This is the copper losses. So if you find out the stray losses, total losses are 1046.4 minus 385.01. So we are going to get 1046.4 minus 385.01 will give 661.39. And the stray losses for each mission will be half of this quantity, 330. It is 661.39 by 2, that equal to 330.69. Now, once you calculate the stray losses for each mission, you can find out the efficiency when it is acting as a mode for a series motor and separately for series generator. So let's see for series motor. So here, so first reading, so V2 into I1, V2 are having 203 into 15.8, 203 203 into I1 is 15.8. So we are going to get 203 into 15.8 will give 3207.4 watts. Now we need to find out the motor losses. So in motor the stray losses we got WS by 2 as 330.69. In addition to the stray losses, we are going to have copper losses. So the copper loss are armature copper loss and field copper loss. So 0.863 is the armature resistance, 0.261 is the field resistance into I1 is 15.8 square plus stray losses are 330.69. So total will become 0.863 plus 0.261 plus 11 square into 0.863. Here we have calculated. So 15.8 square into 0.863 plus 0.261, we are going to get around 280.59 plus 330.69. So we are going to get 280.59 plus 330.69. So total we will get 611.28. 611.28 watts. Therefore, motor output is input 3207.4 minus total losses 611.28 watts. We are going to get 3207.4 minus 611.28 as 2596.12 watts. Therefore, the efficiency will be 2596.12 divided by 3207.4 into 100. That will be divided by 3207.4 into 100. So we are going to get 80.94%. 80.94%. That we have to enter in the table. So here V2 into I1. V2 into I1 we got as 3207.4. And total motor losses we got as 611.28. Next, motor output 2596.12. Next, efficiency we got as 80.94. Similarly, we need to calculate for the remaining 5 sets. So the first set we have made calculations. So remaining 5 sets we need to do the same calculations. So like this, we need to make the calculations for the remaining 5 sets calculations, 5 sets of readings that we have available from the field test. Now coming to the generator circuit, here these are the generator calculations. So here the generator output is given by V5 into I2. V5 is from our field test readings 218, I2 is 11. So 218 into 11 218 into 11, we are going to get 218 into 11, 2398. So this is the output of the generator circuit. Next, total losses. So the series field winding we have connected in the motor circuit, and armature is in the separately. So the armature and series field winding are disconnected, and series field winding of the generator is connected in series with the motor. Therefore, the generator series field winding is going to carry the motor armature current. Therefore, it is I1 square plus armature circuit 0.863 is going to carry I2 current plus stray losses. We are having 330.69 for each machine. So we are going to get 0.261 into 15.8 square plus 0.863 into 11 square plus 330.69. So total is 500.269. So I am taking as 27. 500.27 watts. So generator input will be output. Output is 2398 plus total losses for the generator is 500.27. So we are going to get 2898.27 watts. So the efficiency will be output, that is 2398 divided by input 2898.27 into 100. So we are going to get the efficiency as 2398 divided by 2898.27 into 100. 82.74. 82.74%. Now we need to fill this data in this tabular column. For the first set, we are writing the calculations. So generator output is 2398. And total loss are 500.27. Input is 2898.27 and efficiency is 82.74%. The next second set, similarly you can calculate for second set, and then for third set, fourth, fifth, sixth. So like this, we need to complete for the total 6 sets that we have taken in field test. Once these tables are completely filled, from these table column values, we can plot the performance curves. So by taking the load current as the x-axis quantity, efficiency as the y-axis quantity. So the load current is I2 for generator, I1 for motor. So with the variation in the load current, how the efficiency is going to vary. So based upon I1 and efficiency, we'll get the motor performance curve, and I2 and efficiency will get the generator performance curves. So from the readings of efficiency values and I1, I2, we can plot the efficiency variation. So that completes the field test. And one more thing that we have to remember here, that here, if you observe, the series field winding of the series generator is disconnected from the generator circuit and it is connected in motor circuit. This is the series field winding of the generator. It is disconnected from the generator circuit or it is connected in series with the motor circuit. The purpose is we need to divide the stray losses among the motor and generator. As both are of same rating, if the current through the field winding is going to be same, then we can equally divide the stray losses among the motor and generator. Suppose if the series field winding of the motor and generator are carrying different currents, then the copper losses will be different for the motor and generator fields. Therefore, we cannot equally divide the stray losses among the motor and generator. Then it will become difficult to divide the stray losses among the motor and generator. So, in order to make it convenient to divide the stray losses among the motor and generator, what we are doing is we are disconnecting the series field winding of the generator from its armature, and it is connected in series with the motor, armature and field circuit, so that the field current of the motor and field current of the generator will be same. Thereby, we can equally divide the stray losses among the motor and generator. That completes field test. Okay. So from the efficiency curves, from the tabulated readings, we need to calculate the efficiency of motor and efficiency of generator separately. And from the efficiency values, we can plot the performance characteristics. That completes the calculation. Thank you.